Okay, good morning. Today we're going to give an overview of really what I feel is the focus of the rest of the semester, a transition from the topics and the great deal of material we have tried to address so far in the structure, properties, and interactions among nanostructures to the beginning of thinking about how we can use this knowledge to understand and hopefully in the project propose innovations to nanomanufacturing processes. So I've created this lecture as a new lecture I didn't have it in the past versions of the class to try to create this overview. I'll explain later how I think it really is a midway point in the course, and also I hope that giving us this, starting this perspective can also help to seed some ideas for the project. And with that, I do have a few announcements. The first is I think everyone signed up for the video assignment. If you have not, it means I haven't seen your name on the spreadsheet or you haven't contacted me. So otherwise, I trust that you have formed a team and things are going well. Of course, feel free to ask us if you have questions about the particular topics. Second, I have made some slight revisions to the syllabus, which has been reposted on CTools, and I just want to show that to you right now. So we are here at the start of topic 3, talking about the synthesis of nanostructures with today's overview lecture. Of course, next week is the winter break or spring break, so we have no class. And then the lecture schedule is pretty much as laid out before, only I've made a few changes to the due dates for the assignments. And I had two goals in mind here. One is because I was away on Monday, and because I want to cover some topics before the exam, I have moved the exam date from, I think it was Wednesday the 17th to Monday the 22nd. So the exam review will be Wednesday the 17th instead. Second, we had in the previous schedule kind of bunching of assignments. I was also going to ask for your project proposal, which I'll discuss in a minute, before the exam. Now that is due the week after the exam. And this was a bit of a conflict for me because I want to mentally get the project started as early as possible. So as it says on the project description, I'll take your proposals as early as you want to submit it, but the due date will be Friday, March 26th. And then I will promise to return them by Monday the 29th with comments, and that can catalyze formation of your teams. Question?
Proposal options or?
Yeah, I'll talk about the project in a moment. You can basically do whatever you want as long as it relates to the class. And then, of course, the video assignment is due before the exam. We're also going to use that as kind of a tool for exam review, and I've moved the due date for that. I think it was from Friday or Sunday to Monday. And then after the exam, the goal is really to focus on the project, and there will be one more problem set that'll focus on assembly, and this will be a team problem set. And then all these things, aside from the GCC, relate to the project. Yes?
The peer review of the videos?
No, there'll be peer review of the videos, which I haven't explained yet. I won't be able to talk about that today. That's peer review of a part of the project, which will be described now. So I've also posted, you should have a notification email, a few-page document which tries to give as much of information possible about the project. So our goal is not to read this here, but explain that the project has two phases. The first page is a proposal where I ask you to write and submit a two-page max with references proposal of an idea for the project. And the things I'm looking for, basically a description of your idea and relevant background literature, you know, a few 5 to 10 sites are on this page. And I want you to prepare that individually, even if you have a team in mind. So you may have, you know, people who have common interests, or your team from the video assignment. And even if your goal is to work together as a team on the project, you have to submit an individual proposal. That means that you can, say, submit proposals in the same area. Say, if you wanted a new, you know, process for, you know, growth of silicon nanowires, but your proposals have to be distinct ideas. And part of that, I have two reasons for this. One is I want you to go through your thought process individually. Of course, you can discuss your ideas with others. And second, I feel that, you know, when you decide what you want to do research on or do a project on, it's good to funnel ideas. So I hope that through your discussions and through my review of your proposals, you can decide on a, quote, best topic or hybrid topic from the ideas you propose as a group. On the other hand, if you don't have teammates or are looking to find people who may be on other video teams who have common interests, I'll look at your proposals and perhaps make some suggestions of what things might be compatible. So that's the individual portion. The project total is worth 45% of the course grade, so really almost, majority of the course grade. And your proposal is 5%, and that's individual. And then the second phase is the team effort, a paper, which is 30%, and a presentation, which is 10%. And you'll do team evaluations at the end of the semester to assess everyone's contribution. Nominally, I hope everyone has a good team and contributes equally, and that means you'll all get the same grade. But in exceptional cases, if we identify issues, then we'll talk and we'll address those on a case-by-case basis. But and if you are having team issues, I'd like you to come to us ahead of time rather than at the end. We'll do our best to make sure that we have a productive group work experience. So the second phase is a report and a presentation, and my details for specifications are in this document. Just look at it and please ask if you have questions. And there's a schedule of due dates culminating in presentations, which will be on Monday evening, April 19. I like to have 3 hours for the presentation, so we have enough time for 15 minutes per team, and then the next day reports will be due. And prior to that, we will have a peer review activity where on Wednesday, April 14, a one-page summary and figure, sort of your draft summary for your report and your outline are due, and those will be not for my review, but for review of other teams. And I'll give more details of that. And 2 days later, you'll be required to submit to me and to the other teams your reviews. So I hope that by that type of extended collaboration, you all can give each other feedback on the clarity of the presentation of your ideas and end up doing better on the report and benefiting from each other's feedback in the end. Okay, so now to the idea of the project. I really want it to be an open-ended project and offer you the opportunity to choose pretty much any topic that relates to the class. And basically, I want you to take the concepts from the course and use them to propose a new idea relating to a new type of nanostructure or material, or a new process for making nanostructures or related materials, or a device that incorporates nanostructures. And in this document, I have some further descriptions of those three categories. Certainly, you can propose something that fits in another category. I just want you to be able to anchor it to the class. And that doesn't mean that you're going to be able to find everything you need in terms of anchoring it to the fundamentals from the course material. I'm sure in every case, there'll be some areas where you'll have to dig a bit deeper, and we'll get to talk about those. Through the proposal, I want you to propose your ideas. Sometimes this is a challenge to start. I say you can do whatever you want, but start from what lectures you've enjoyed the most or what topics are most interesting for your research or possible research, and we can go from there. So, for example, I'll take us through one of these areas. So, if for example, if you wanted to propose a new type of material, for example, you wanted to propose a type of nanowire that maybe has some complex variation of its geometry along its length. You could propose this material, and this could be an individual structure, or it could be a larger architecture, an assembly of structures that would have interesting collective properties. And I would want you to build some basic model of the relevant properties and how the properties scale. And then I would want you and your team to design a process for fabricating the material and discuss how you would characterize it, and then discuss potential applications. And in all topics, a really important thing, as if you were writing a regular research proposal, is to benchmark what you may expect. I mean, there are always going to be uncertainties because this is a new topic and you haven't done research on it yet, but benchmark it against existing materials. So, for example, you think this material would be very useful in, say, a solar cell. You would want to make some comparison to existing materials and existing emerging approaches to using nanostructures for use in photovoltaics. And this will always be on a case-by-case basis, depending on what you choose and depending on what the topic of your project is. And I have similar things in the other two categories that I offer for organization. And then at the end, I suggest themes or topics that might be found in your report. And I want this to be well anchored to the background literature, well anchored to the course, and be a clear communication of analysis you do in relation to the subjects and specific goals of research that you would like to conduct in the future. I wouldn't say we're writing a research proposal as if we're pretending we're proposing a project to an agency, because I want to tie the subject to the class, and I want you to explain how it's clearly tied to the class. But I think it's a good exercise to look, for example, at guidelines that funding agencies have, and I have a couple links here to NIH and to the National Science Foundation and to a project by the Defense Department that we'll talk about today. When agencies ask for research proposals, they're very clear on asking you to explain the novelty and the specific goals of your work, and that will be an important part of this report that you prepare. And I know things always tend to end up at the end of the semester, but I encourage you to, over the last month of the course, when you're in your teams, try to distribute the thoughts about this as much as possible. Things may inevitably come together within the last week, but if you get yourselves thinking about and answering key questions and dividing up the work early on, I think it'll be a lot easier and a lot stronger in the end. Because when you're working with what you hope is a new idea, critically questioning yourselves and looking into the literature will lead to probably a lot of deconstruction and reconstruction and evolution over the course of the month. And to keep in touch about your topics and what you think the specific expectations for your topic are, I'll set up meetings with each team. I'm hoping for at least 2 meetings, one right after you form your team and choose your topic, and one in the week prior to the final presentations, maybe 15 to 30 minutes a team. And this is not spelled out. I'll probably add it to the project description. But there are 2 things I want to make sure of. You're most welcome to suggest something that's a research interest of yours. But I don't want you to propose something that is very close or exactly your current research. And if you have concerns about that, come talk to me and we'll discuss it. Basically, I like to offer the freedom in a course project to sort of extend what you're already doing, but I don't want it to be something that you're directly doing already. Likewise, if you're taking other courses, I don't want you to double up this project with a project in another class. And if there are particular concerns, please come talk to me. And if you have a question or want to say, look, I think I can do it, I can add these 2 but keep them separate, then I hope we can come to a good ending point. Okay, are there any questions on the project description? So if you're taking off for the break next week, please take a look at this beforehand and get your thoughts started. And also, I'm going to post the 3rd problem set by next Monday, and that'll have 1 problem on plasmons, and then it'll have the rest of the problems on the material we'll be covering in the next couple weeks. And last, I took a look at the midterm evaluations, and you all had some questions about the amount of material we've covered in the class, which I agree is a lot, and what the expectations will be going forward. So in consideration of the exam, the midterm exam, and the GCC, if you're taking that, my expectations are certainly not that you'll be responsible for everything that you've read and everything what you've read refers to. I feel the heart of the course focuses on the content of the lectures, so the concepts that we discuss during the lectures, as well as the things you're asked to do, the specific execution of those problems on the homework assignments and the concepts therein. And I feel that if you feel like you've mastered the homework and looked at the solutions and understood the solutions and gone over the lectures, a good way to study is to watch the lectures again and go through the notes, that represents what I'll expect you to be able to communicate on the exams. And I think it's a challenge that there's no specific textbook for this class, and I think by the nature of the field it forces us to grab a lot of information, and I appreciate all the reading you've done, but I hope that we can try to keep the focus on this going forward. And also, I think that we're kind of crossing the bridge into the part of the class where things will become more practical, and hopefully we'll be able to look back to the things we've grabbed from before and be able to integrate some of the knowledge and maybe get a better understanding of the relevance of the things we've discussed already. Okay. So quickly, last time we talked about our last specific topic of interactions, and we talked about the idea of surface plasmon resonance, or at the simplest level, interaction between light and metal surfaces. And this exists for surfaces of metal, and it exists in a more interesting level for us for metal nanostructures. And when the resonance of charge moving through a nanostructure matches the frequency of the electromagnetic field or the light that's exciting, these electrons in a structure, you get what's called a surface plasmon resonance. And this is an effect that depends heavily on the size of the structures, their shape, and on their environment. And there are some really complex relations in that really were beyond our scope and also our cutting edges of research. But a couple of important concepts are that this environment, this effect being very sensitive to small length scales of the structures, and the environment means that it can be used as a very effective sensor. And for simple geometries, you can use electromagnetic theory and specifically me theory to calculate the frequency of this resonance and, for example, see how it scales. And one of the examples from research we discussed, this was a computational part of a paper that modulated the distance between two metal nanostructures, showed that the scattering intensity spectrum was a function of the distance between the particles. And that concluded what I initially laid out as part 2 of the class. And when we come back the Monday after the break, we're going to talk about nucleation and growth, which again is a subject that has a bit of thermodynamics and kinetics in it. But I'm going to try to get us to start to establish a real manufacturing perspective, thinking about things like precision and errors as we think about how the sizes and characteristics of structures evolve during a process and how those relate to properties. And then after we talk about synthesis, we'll have the exam, and we'll talk about assembly and scaling of properties, and then we'll close it up with the presentation and the project. And despite the emphasis of your project, whether it be say a material or a process or a new type of device, you'll see in the way I laid it out, each project will talk about a manufacturing process, how you're going to make it, whether you're going to make it in the lab if it's something new, or if you're proposing a large-scale process, how you're going to think about the scalability and manufacturing characteristics of that process. So really, I hope that the project has both a manufacturing emphasis and a fundamental emphasis, tying the principles from the first half of the class to the theme that you want to investigate. So the focus of today's lecture is to kind of frame our thinking from this top-down and this bottom-up perspective. And on the first day of class, I showed this slide that tried to contrast at the ultimate level what we refer to as a top-down process, where we take, say, a piece of material and create some information in it or features by removing material. And we're not talking about milling in this class, but and it's an example of a classic top-down manufacturing process where material is being removed from a larger shape. And at the opposite end, we have what we classically call bottom-up processes, for example, taking individual molecules, and by engineering specific interactions between molecules and, say, a substrate, we could build up a material with a greater degree of complexity. So we could, for example, order these in a layer, or, for example, these, in a real, concept were metal structures. If we had some way of programming the interactions between the metal structures and the substrate, and say more metal structures than the previous ones, and turning those interactions on and off with time or with a space, maybe we could make something as big as this. Wouldn't necessarily be the most efficient way to do it, but if, for example, we get down to a scale where we can no longer mill a very small feature, gee, that may be a way that we can bridge the gap. So the course of microfabrication and nanofabrication and chemical synthesis and chemical self-assembly is something way beyond what we can cover in good detail in the next few weeks. But in this course, we're going to focus on these types of bottom-up methods for synthesis and assembly of nanostructures, and are going to emphasize how they integrate with top-down methods, things like lithography optically or using electron beams. And I really feel it's the convergence of these approaches that's going to enable practical realization of nanotechnology and nanodevices. We're going to take advantage of our ability to structure things using techniques such as lithography that have been developed for decades and are getting better and better as we see, and we're going to complement those with control of the assembly from the bottom up. And I want us to really, in every lecture, in every assignment, in every project, rigorously question the limitations of these methods for true nanomanufacturing. I mean, we've already realized that it's a long way until we reach the ultimate goal of precisely placing structures, with type and orientation and position and mixing them. But if we understand these methods, I think we can hopefully realize how we're making progress toward that end goal. And when we think of real manufacturing or nanomanufacturing, another slide from the first day is this one from Lockheed that does a lot of large-scale materials fabrication and is interested in electronic devices for a lot of applications. And they look at so many things that we really think about in classical manufacturing. Cost and automation, and the ability to integrate modeling and simulation tools, and the ability to make interfaces to structures, and the ability to scale them up and characterize them, and also to calibrate the structures and have standards and so on. So all these things are at play and are coming into this field as we get more understanding of these processes at the scale. And in the end, what drives a business, what drives a practical realization of a material is, they boil it down to, economics in terms of cost, in terms of health and safety, environmental health and safety is EHS, and in terms of the ability to get a high throughput. If you didn't have all of these three, you wouldn't have a feasible product in the end. And while we don't focus on that, it's a good thing to keep in mind when we benchmark these different processes. And for example, the effectiveness of lithography to make computer chips and microelectronic circuits is enabled by advances in all of these three areas. And because that meets all of these three objectives, then so much investment has been invested in development of the technology and has enabled further progress along these lines. And I would just like to say that I feel that one of the specific challenges for nanomanufacturing and integration of nanostructures or assembly of materials is this idea of calibration and metrology, and really understanding how you control order and perfection, because you need to understand where the defects are, where the flaws are, and how those flaws propagate and relate to the structures of materials. And while a lot of things are possible from what we do now, that to me really is an area that needs a lot more work and will drive the field. Just as characterization and metrology are one and one, in my opinion, has driven the ability to do nanoscience and turn that into nanotechnology. So I just have a couple readings. One is a chapter from a book called Introduction to Nanoscience on fabrication methods. And it's kind of like the characterization paper I gave earlier. It doesn't have complete information, a lot of things, but I just want you to read it as a survey to accompany the lecture. Specific techniques that are emphases for us will be talked about in subsequent lectures. And then I have pages of a BAA or a call for proposals from the agency DARPA, and I'd like you to look at the first 10 pages, which we'll talk about in a moment. So this is what I'm going to talk about now. And so government agencies that fund research are interested in advances in nanomanufacturing because they feel that if we can make materials and devices more precisely, we can enable a bunch of applications. About 2 to 3 years ago, the Defense Advanced Research Projects Agency, called DARPA, announced a program called tip-based nanofabrication. It refers to their interest in using scanning probe tips to advance our ability to assemble materials, things such as nanotubes, nanowires, and nanoparticles, or quantum dots. However, they really did it because they have general interest in nanomanufacturing in general. So they announced this program, and the goal was to get ideas and get proposals from teams of universities and companies to establish what they call nanometer scale control over the size, orientation, and position of individual structures. And their idea, which I feel is correct, is if you had this capability, we could build real technologies based on these materials. And if you can establish these goals on a large scale, then you can really, for example, realize massive arrays of transistors that, say, use nanotubes or quantum dots, just as we can create large areas such as full wafers of circuits for manufacturing of microelectronics nowadays. And the way this program was conducted and is now running is they said that you have to, in your proposal, describe how you're going to meet specific quantitative metrics. And so if we look at just the first 4 rows here, they said that the program, they're going to give funding in a few phases. And if you get funded for phase 1, you're going to have to demonstrate that you can control the position of features within an accuracy of 50 nanometers. You can control the size of those features within 10% of that dimension, so so 50 plus or minus 5. And you should be able to control the heterogeneity of those features. So maybe that means you have, two sizes of features. You can make a 50 nanometer feature and a 25 nanometer feature, 50, 25, and so on. Or maybe you have two 50 nanometer features, but you can make them out of material A and material B. And you can clearly see that this is perhaps exceeding the capabilities or issuing challenges beyond, for example, the ability of lithography to make very small features. As we'll see later, lithography can meet these means, but have them be in one material. And they also placed restrictions on the rate of where the features are formed. For example, the formation of one feature per minute. And this is, if you think of lithography, you can make billions of features a minute, and this is not typically a challenge. But when you do things like combine two features or two types of features at once, it can be difficult. And their idea, and it turns out the projects they funded really focused on this idea of a tip-based manufacturing, from which we'll see examples later, and they were interested in the number of tips that you used and the variation in the shape of the tips and the ability to sense the height of the tip and so on. But their general aims, they said they would fund anything that meets these goals. And with time, they said that if you stay in the program, if you meet these targets within phase 1, and we like what you're doing, then we'll give you another phase of funding, and you have to get tighter in all the requirements and do better with time. And I don't know the specific results from this program so far, but I think they're about in this time frame. But why I'm describing this is I thought it was a really nice example of definition of their perspective on nanomanufacturing, which I think adequately expresses the challenges that we want to talk about from now on. So they define controlled manufacturing as a parallel fabrication of individual structures with control over their position, size, shape, and orientation at the nanometer scale, and the ability to fabricate devices with controlled differences in size, shape, orientation at different positions. And it should include the ability for in situ detection of these characteristics and the ability to repair or remanufacture the structures as needed. So it's all the type of things you can envision are possible if you take a block of material and mill it out, but applied to these very fine length scales. And a lot of the things that we could talk about today, such as lithography, can maybe do that on larger scales, but can't do that at the nanoscale. And a lot of processes to self-assembly, such as building monolayers on a substrate or assembling three-dimensional crystals using electric fields, magnetic fields, or capillary forces, can meet these nanoscale size constraints and maybe can incorporate particles of different shapes, but are really not able to, say, put different things at different arbitrary positions and control things like orientation. So they were really, to me, expressing a challenge that is a long-range one and is the essence of controlled manufacturing at the nanoscale. And they said, well, gee, we think that presently this aspect is not possible, and there have been a lot of demonstrations, like the things that we show slides about here, to grow, deposit, or manipulate structures, but they all suffer from deficiencies when viewed against the above stated goal. And so they gave a couple examples here. For example, one where you can make quantum dots by a lot of methods, but they thought there's no means for controlled manufacturing of patterned arrays of two types of structures. And there's no ability to repair the non-uniformity from these typical processes. So maybe you can make an array of one type of structures by a bottom-up method or by a top-down method, but there's not an ability to place two types in that array, A and B together, or A, B, C, whatever you want. And further, when you look at research on this topic, there's a lot of great work, but you can often clearly see that there are defects, missing dots, or if you have a lattice, there'll be a dislocation, and the ability to control those things is inherent in having uniform properties and in scalability. And they said that none of the presently emerging approaches appear to provide a path to controlled nanomanufacturing, and I think that's true in the context of the definition of a lot of the things that we will talk about, and that to me really states the challenge and how we want to learn and move forward. So to see these goals again, they were really trying to push the idea of high throughput, like Lockheed wanted, and heterogeneity, having multiple values of multiple parameters, or continuous control over multiple parameters, say dynamic variation of size. And if we think about this a bit more, we realize, gee, this is really hard to do. And maybe the folks involved in the program will generate some really useful results, but may not even meet these goals. But that was probably what they were trying to get people to do to stretch their limits when they put this proposal call out. And they also said that they wanted to think about a whole bunch of individual features. For example, they were interested in ideas that, say, could control the chirality of carbon nanotubes. And when we talk about nanotube growth in a couple weeks, we'll learn that carbon nanotubes grown have a broad distribution of chiralities, but there's no practical way to grow just one specific chirality, even just to get any one chirality, let alone to choose the chirality of nanotubes you want to grow. Or other important things are methods that don't require specific substrates or heavy constraints on the process. It's possible to grow certain types of structures on say specific crystals that have specific interactions with, say, the material you're depositing from the vapor. And that works in some cases, but nothing is nearly as versatile as lithography on a silicon wafer, where you can combine a lot of different types of materials together. And as may be expected, they were also interested in the ability to combine these nanomanufacturing approaches with pre-existing structures and devices. And foundry CMOS refers to CMOS being complementary metal oxide semiconductor, or basically clean room fabrication for microelectronics, where they say that the conditions at which you make these nanostructures have to be able to work with integrated circuits. Because if you have a device that wants to be electrically addressed, it's even more of a stretch to imagine that you'll be able to use your process to fabricate the whole thing. It's a much more practical approach to say, I'm going to make some nanoscale element or assembly of nanoscale elements, and then I'm going to address it, talk to it, control it with a circuit architecture that can be readily made using existing fabrication technology. And therefore, the approaches that you devise have to be compatible with that. It's kind of like what happened in the field of MEMS, or microelectromechanical systems, where in the MEMS field, integrated circuit fabrication technologies, thin film deposition and etching, were used to create mechanical and electromechanical structures. And then for things like the first MEMS devices, like accelerometers that are used for airbag deployment, for example, nowadays, you have a mechanical device, an electromechanical device, a moving mass that moves in an acceleration field, and that's surrounded by all the circuitry, the low noise electronics that measure the signals from the motion of that, and that's all made in the same process. And that, in addition to all the process control and characterization, is what made those devices feasible. So, that's what they're saying is important in the end here. Maybe that's specific to things like sensors and electronic devices. Maybe it's not true if you just wanted to, say, self-assemble a bulk material, or say an optical material that would not have an electronic functionality. But it is a very important consideration in the context of some of the devices that they envisioned. Okay, so for the rest of the lecture, we're going to go through some top-down methods for pushing the feature sizes of the material removal process, and then we'll talk about some examples of the integration of top-down with bottom-up methods. And the formal definition, you could say, of a top-down fabrication method is one that begins with a bulk material and subsequently reduces this material into nanostructures, the top to down, by the way of pretty much any process. It can be a physical process, a chemical process, a mechanical process, or if if there's another category, that can be added there too. And it's always difficult to categorize processes by these themes, but one attempt is made by the book chapter that we're reading, and says examples are, say, mechanical processes, milling materials, extruding them, grinding them, processes that use thermal energy or chemical energy or high energy interactions, such as with electron beams or X-ray beams in materials. So examples of this could be evaporation or sputtering. Some of you may be familiar with what's called physical vapor deposition, so taking a bulk material and heating it with an electron beam or impinging it with an ion beam and creating a vapor of that material, and that is a means of, say, creating nanostructures in the gas phase. And those could be collected on a substrate or collected into a bulk powder and so on. That could be, say, classified as a top-down method, taking a big material and converting it into smaller parts. Other examples are reactive and chemical etching, say using a plasma or using a chemical to etch features in a material, for example, using a mask. As we'll see in the case of lithography later, etching processes drive the ability to to use photolithography to create structures in other materials. And there are other kind of bulk methods you could think of. This is very coarse, just creating, say, large powders, but they're effective, for example, for making 500 tons of carbon nanotubes a year in industry today, combustion or sonication for having energy in a liquid bath. And then another classification, which maybe kind of fits in the other category, but I'd like to divide them out because we'll talk about them specifically, are methods of establishing patterns. For example, using optical lithography or physical lithography, imprint lithography, or using the concept that DARPA was trying to extend, using very sharp tips, scanning probe tips, to fabricate structures. But the common theme here is that you take a starting material and you end up with finer features in that starting material when you end. So the reading talks about, tries to give a very general introduction to top-down processes for making nanostructures, and it says the simplest process is what's called ball milling, and that's the idea of, say, taking pieces of a material. They could be, say a microscale powder of a metal, and putting it in a rotating drum. And in this rotating drum, you have a bunch of ball bearings, and it's kind of like tumbling rocks. And because of the kinetic energy transfer between the moving bearings and the material, it's actually a means of producing small structures. So just grinding this, deforming it, breaking it, heating it into very small structures. And it doesn't have a very high degree of control, say, of the standard deviation of the particle size you retain, but there's a lot of results in studying the ability of this process to grind, to divide larger materials into smaller ones. And this is a TM image of some zinc structures that were created from a larger powder after 5 hours of kind of tumbling like this. And this isn't something we'll talk really more about, but I wanted to make the point that in this case where you're kind of pounding something with a ball and making it into smaller structures, there are a lot of different energetics at work here. You're deforming the material, you're breaking bonds, you're, because of friction, you're dissipating energy thermally locally, and there are a lot of very small-scale interactions that maybe this process isn't controlling, but are important to determining the size and shape of these structures. And you could envision a lot of the other processes we'll talk about as trying to kind of isolate one of these interactions or have better control over one of these interactions to make structures more precisely and in a more organized fashion. But in principle, you can make things small just by taking something and dividing it up in the most brute force way. And a couple other examples of kind of bulk top-down processes are methods that were initially used to fabricate carbon nanotubes or to grow carbon nanotubes. This is also what's been used to make a lot of other types of nanostructures. And one of these examples is what's called arc discharge. And in this case, you have a vacuum chamber that's sealed and runs at low pressure and is filled with inert gas, such as helium. And you have two electrodes, an anode and a cathode. And between those, you apply a voltage. And you apply a voltage between these two electrodes and control the separation such that you get a short or you form an arc across the electrodes. And in this high energy process, because of the heat here, you end up evaporating some of one of the electrodes. You end up evaporating the cathode, and you end up attracting particles to the other electrode. And it turns out that if you're making these electrodes out of carbon, because of the heat and the field here, you will get precipitation of some carbon nanotubes from this arc discharge. And this is one of the first ways that nanotubes were made, although it had very poor control over the characteristics of the tubes, and also you had a lot of amorphous carbon in addition to the tubes that you wanted. But it's a sort of fairly simple method where you are essentially taking a solid graphite electrode and you're converting it into some more ordered nanostructures. And then another example of a top-down method that's been used to make nanotubes, or in fact a lot of other types of nanostructures by a similar method, is instead of using an arc to, say, vaporize the material or to introduce energy for it to reorganize, you use a laser to evaporate a target. And in this case, you have an apparatus where there's a tube furnace here. So this is, for example, a quartz tube inside an enclosure that heats the tube, say, to about 1200 Celsius. And then this is all in an inert atmosphere like we saw on the previous page. And you take a laser and you turn on the laser to heat a spot on this target. For example, in the case of nanotube growth, is made from graphite. It can also be made from a mixture of graphite and metal. And although this temperature is high, it's not high enough to evaporate the graphite. And so the impingement of the laser upon the target evaporates the graphite locally, creates a carbon vapor, and then carbon clusters, solid clusters, condense in the vapor stream. And if you get the conditions right, this happens very fast on the time order of milliseconds, you collect a different form of solid product downstream. And to, you could say, collect the structures in a relatively efficient fashion, you typically have a cooled collector down here at the end. And it turns out that under the right conditions, you can precipitate nanotubes by this process. So kind of evaporating a bulk material and precipitating a solid of a different form. And this has been used back in the day and still today to a small extent to produce carbon nanostructures for research. But this produces very small volumes and is relatively impure and not very scalable. And we'll see a lot of comparisons between chemical vapor deposition, which is the process we'll study, and these processes in a couple lectures. So I just wanted to give those a couple examples of how you can make bulk disordered structures by processing of a starting block of material. But you could say one of the constraints of processes like that is that you don't have control over the even the position or the size of individual structures, other than creating a disordered bulk, which also has in a lot of cases a lot of impurities or a broad size distribution. So perhaps the most versatile top-down process, which if it had ultimate resolution would be highly useful for making nanostructures, is what's called lithography. And lithography, just by definition, means pattern transfer, meaning transferring a pattern from one material into another material and copying that pattern over and over to create large areas. And for those of you who may not be familiar with the classic process of photolithography, I wanted to show this. This is a diagram that shows the means by which you typically create patterns of features on a substrate. Typically from electronics fabrication, it's on a silicon wafer. And for example, you can start with a substrate, which is often a silicon wafer, and you may have two films of material on that substrate. So the first, the purple material, is what we're calling the target material. So that's, in the end, what you want your pattern to be in. And then above that, you have another material, which is, for example, photosensitive, which means that if you expose it to light in certain areas, you can selectively stabilize it or selectively remove it. And then you can use another technology to transfer that pattern into your ending purple material. So a typical lithography process will use, for example, a mask, so another substrate in which you've made this master pattern, and say, for example, use electromagnetic radiation, say light, to shine, to apply energy through this mask pattern to your photoresist. So if you're using, say, visible light, you'll have a traditional photoresist, and this mask will be, say, a glass plate with a patterned a film of metal on it. And in the areas where you have metal on your mask plate, the light doesn't go through. And in the areas where there is no metal or the glass plate is clear, light goes through. And you can have different types of this resist material. For example, if it's what's called positive resist, it means that, that the material is kept where you have not exposed it to light. And if it's negative resist, it means that it's kept in the place where you do expose it to light. And what actually goes on here is you shoot it with light, you expose it, and then you say dip it in a chemical which will selectively dissolve the area that has not been stabilized by the interaction with light. So that's what's called development. And if you have a positive resist, then you want to expose to light the areas that you want to develop away. And then after you have this pattern in your resist, then you etch into the next layer, for example, using a chemical or using an ion etch. It could be, for example, exposing it to a gas or a gas with an applied voltage to accelerate the ions toward the substrate. And then you can create the structure in the second material as well. And then you could, for example, do what's called strip the top layer, remove it. You could dissolve it in a chemical that just removes the photoresist, and then you end up with your pattern in the bottom substrate. And in the context of visible light, the practical limitation is, as we talked about in optical microscopy, about the wavelength of light. But as we'll see, the innovations of the microelectronics industry have really pushed this process to farther and farther limits. And it's the limits, the limits of all aspects of this process, and most fundamentally the feature size that you can achieve, which to me is really the limits of top-down fabrication. And another comment is that, while it's possible to achieve, very small features in plane, if you wanted to make, three-dimensional structures, things with, say, different shapes, say, curves like this or tapers, it's a bit more difficult, or at least is more time-consuming. So that's another consideration which you would entertain when thinking about how to make any structure of a particular size. Just as you would think about, having a one-axis process or a two-axis milling process or a six-axis milling process where you could, in principle, mill out any arbitrary three-dimensional volume. These processes are inherently planar and additive, or inherently planar and subtractive. And one other consideration in the general process of lithography is whether you use a mask, which lets you process a large area of structures at once, or you use a direct write approach. A direct write approach, for example, could be having, instead of a large field of light, having a laser beam that would just expose one spot at once. And there are ways you can do direct write lithography without a mask. And in terms of the resolution that you can achieve, if we say that it's limited by the wavelength of radiation you use, one way to improve the resolution is to decrease the wavelength of the radiation. So if you have the right mask material and you have a resist that is sensitive to your particular wavelength, then you can, for example, use radiation with lower wavelengths, ultraviolet light instead of visible light, X-rays, or electron beams. And we'll see some examples of that as we go forward. So this is typically done on large silicon wafers, and the sort of driving dimension that you'll see referred to in literature about microelectronics is what's called the half line width. And in a general sense, if you think about making a circuit and having a circuit be an arrangement of wires on a substrate, they typically refer to this number as sort of the quote technology of the lithography as half the pitch between consecutive lines. And so if you hear Intel, for example, talk about making a process with 65 nanometer technology, it means that 65 nanometers is half the smallest dimension they can achieve between consecutive lines in their process. And by poly, they mean lines made out of polysilicon. And this is, for example, a cross-section of a transistor made by an existing process, and you see that it has different materials on the length scale of tens of nanometers. So we'll see how they're able to do this. It's sort of right at the interface with what DARPA was talking about, but it's still not down to the scales that we really need for true nanomanufacturing. So one of the ways that the industry has extended the resolution of lithography is basically using a lot of optical tricks and optical theory. And one of the ways, in addition to reducing the wavelength of light, for example, from visible light, which is, say, 400 to 900 nanometers or so, to ultraviolet light, which has a wavelength of about 200 nanometers. And another way that they've done it is to engineer the optics and engineer the optics that are used for issuing the light onto the wafer in a fashion called immersion lithography, where they put a liquid between the lens and the substrate. And if you have a liquid that has a refractive index greater than 1, then you can reduce the effective feature size that you can expose onto the wafer. And if this liquid is compatible with the other elements of the system, it ends up being a very practical process. And for example, you have a lens here like so, and water can be a typical fluid, although now to improve the, if you increase the refractive index by this method, the higher it is, the finer the resolution that you can achieve. If you have other liquids or immersion materials that are compatible with the substrate and the process conditions, then in principle this process can do better. But things like permeation of the resistant to the substrate, or the temperature at which it evaporates and how well it wets the substrate, all those kind of principles of wetting and surface energy are all important in a case like this. But this is one of the ways whereby lithography is being pushed to finer and finer limits, by engineering the optics and the wavelength of light that interact upon the substrate. Another type of lithography that's used widely and is more so in a research basis than a production basis is e-beam lithography. So now there's probably a limit to the length scale to which we can use light to do lithography. And if you change the beam to something that has a smaller wavelength and can be focused itself to a smaller spot, you can achieve finer features. So by using an electron beam for lithography instead of light, you have a process that is practically limited by the size of the electron beam you can create, which can be a nanometer or smaller, and also by the interaction between the electron beam and your photoresist and the material you're trying to pattern. And it turns out that the scattering of the electrons in the resist are a more practical limitation, and that means that you can achieve features below 20 nanometers, and I'd say down to the size of a few nanometers. And this is just a schematic, for example, of, it's kind of like an energy carrier scattering process. When an electron hits a material, it can go into a small volume within the point at which it hits, and the mean free path of electron scattering in this material actually determines how well you can localize your electron beam process. And this is a chart which shows the mean free path as a function of the electron energy, and if you use a beam with higher energy, you'll have a smaller mean free path of scattering in the material, and you'll be able to achieve a finer spot. And this is something that can be done using even a scanning electron microscope, by focusing the beam and exposing a material that's sensitive to electron exposure. There are some polymers such as PMMA that are good for this. But inherently, a limitation of e-beam lithography is it's a serial process, because you need to raster the electron beam over the substrate and create the features by individually writing them. You don't have a big mask that can do a large area at a time. And this is what has really prevents electron beam lithography from replacing optical lithography as a means of patterning materials. And so an example of the difference between using optical lithography and e-beam lithography to, say, grow nanostructures is, say, the picture on the left is where, as we'll see later, optical lithography was used to create micro patterns of catalysts that grew forests of carbon nanotubes. So each of these is a block of a lot of nanotubes aligned vertically, kind of like that. This is far from the lower limit of optical lithography, but gives an idea of kind of a micro-scale area where the nanotubes then self-organize to form a structure. Something at the opposite limit is, for example, using e-beam lithography to pattern individual dots of metal catalysts. So you could see that this area contains a random arrangement of all these dots, and then growing individual nanostructures. These are kind of cone-shaped nanotubes from each of these dots. So these are kind of two processes at opposite limits that use two different types of lithography to then execute an inherently bottom-up process, which is the growth of the nanotubes from the catalyst particle, which relies on the self-assembly of the individual atoms from the gas phase into a structure, as we'll see later. And another kind of prototyping process that we saw before, just to show it to you again because I think it fits into this category, is you can use use beams of light or electron beams to modify materials. You can also use beams to physically remove material, and for example, focused high-energy beams of ions, called focused ion beam milling, can be used, for example, to cut materials at the small scale. And this is, if you remember, our example of, say, taking a structure which could be a circuit structure made by lithography and slicing it up so it could be examined using a transmission electron microscope. And you can do a lot of very versatile things with a focused ion beam, but because it's an inherently serial process, it's really not high throughput. Incidentally, in microelectronics fabrication, one of the most expensive components is the mask. Because they're creating such fine features, they have to create and want very low defect densities. They have to create very accurate masks for really big wafers. And so electron beam lithography is often used to create that master, and focused ion beam milling and focused ion beam deposition of materials is often used to repair defects in the mask. Or if, say, there's a particle on the wafer and it damages the mask and they detect that by examining the circuits, they often take the mask and they repair it with these kinds of lower throughput techniques. So it's kind of like a nanoscale repair process that complements the larger area methods. And one of the things that's been observed and is kind of talked about in the scalability of top-down processes is what's called Moore's Law. And you may have seen this before. It's called Moore's Law because it was proposed by Gordon Moore, who was one of the founders of Intel. And basically his observation in like a few decades ago was that because of advances in microelectronic fabrication, top-down lithography, the number of transistors that we could fit on a particular area of circuit was basically doubling, I think, every 2 years. And if it doubles every 2 years, it's an exponential growth, and it means that it's a line on a log scale. And the numbers here aren't important, but the idea is that, for a long time, we've been able to improve lithography processes to achieve more computing power per unit area. But the big question that's been going around for a long time is, when is this trend going to end? Because you can't take these processes down to zero. And this is another way to look at it that Intel puts out, where instead of having like number of transistors directly, they relate it to the processors that they put out. But it shows that there are different models, such as different Pentiums, have effectively packed more information over the same area, which means that that line width is decreasing. We're understanding how to use these processes to create smaller and smaller dimensions. And so where we are now is having the industry is having a big debate as to where optical lithography is going to end, and where we're going to need to include, or will be able to include, processes such as self-assembly and imprint lithography to create finer features and to create some of the complementary things that we'll hope to talk about in the next few weeks. So this is kind of a complicated chart, and it's from the but what it does is it's plotting versus time, starting now, a projection of the expected line width, or that official feature size, that is going to be achieved in industry by various methods. So it says that by, say, at the other limit, 2020, we're going to be making circuits with a half pitch of about 10 nanometers using EUV, which is extreme ultraviolet lithography, and using imprint lithography, and using self-assembly as well, perhaps to create different types of features. And this is put together by, it's called the ITRS, or the International Technology Roadmap for Semiconductors. It's interesting if you're interested in this topic, a consortium of the companies that work on the machines and build the chips, and talk about the future of, as things which drive the whole industry. And basically what they're saying here is that optical lithography, using all of these special methods that have been developed over the past years, will run out at a feature size at a half line width of about 20 nanometers. And that's when we really need to integrate more advanced bottom-up methods and other types of lithography to complement the top-down methods. So honestly, this line is being, as people get better at lithography, it's being pushed ahead from year to year, but it's pretty likely that this is close to the ultimate limit. Is there a question?
For the interference lithography, are they talking X-rays?
They can use X-rays, and you can also use beams of light. It depends on the particular process. But then if you have, basically, I don't have that in the lecture, maybe I can show at the beginning last time, you use two two beams, and by interference of those beams, you can create very fine patterns. But there is a restriction to the types of patterns. Typically, you can only create lines. You can create kind of like sinusoidal fields using those methods. But that's another way of improving the resolution of lithography. So one of the really most practical methods that is certainly going to make it and help out the top-down world is what's called nanoimprint lithography. And it's the same principle of lithography as we saw before, but instead of using radiation to pattern a material, you use a physical method. So it's basically nano stamping. And it was invented by Stephen Cho's group at Princeton about 15 years ago. And here, your mask is a stamp. And so you use, for example, say E-beam lithography to pattern a stamp that has features of the size that you want. And then you, for example, use it to imprint its shape into another material, say a polymer that's heated above its softening temperature on a substrate. And as you can imagine, this requires detailed understanding of the forces needed to imprint the polymer and, say, the surface energies between the stamp and the polymer. But in the basic case, you can use this method to physically transfer small features to a second material, and then, for example, you can use this imprinted material to pattern a second substrate, or you can, say, deposit, for example, by electrodeposition, if this is a conducting material and this is an insulating material, features in accordance with this pattern. And as you can imagine, the fabrication of the stamp, so whatever you use to make your master, is a limitation. And also the properties of this, the imprinted material, which we can still call the resist material, are limitations to this process. And by doing things like making over very small areas very fine stamps, you could think of also, say, using a nanotube or a nanowire as a stamp to show small feature capability. This has been shown to work for features of less than 5 nanometers. And it's an interesting area, like how accurately can you eventually imprint small materials. And another interesting aspect of this is because it's a physical process, you can think of it as possibly being implementable on large areas. So in fact, Jay Groh's group here in electrical engineering is one of the leaders in this field, and they recently published a paper where they have a prototype machine to do continuous nanoimprint lithography. So here's an example of a scalable nanomanufacturing process. They're not achieving 5 nanometer features, but they're able to create very rapidly large area patterns in imprintable polymers. And so, for example, let's take the bottom picture here. They, for example, have a hard substrate. It could be, say, a glass plate or a silicon wafer on which they have the resist material. And then they've created a flexible stamp in the form of a belt out of, say, a harder polymer or another material. And by continuous feeding of this belt over this substrate sitting on rollers, and by exposing the material to light, in this case, you're effectively curing the photoresist in the areas where it still remains between the grooves in the template. They're able to then create features that replicate the stamp. And this is a more, you could say, sophisticated or involved setup where they are transferring it from one flexible film to another, and also have a means of applying this resist in a continuous fashion from a liquid bath. And I think this is actually what they were doing here. And for example, they showed that it can be used to print these kind of sub-micron gratings. This is about a half micron by a few hundred nanometers on polymers that are on glass plates over pretty large areas. So I think it's a really nice result that shows the potential of this technique to do things rapidly and scalably. And innovations in this technique will, certainly, if you can take these features and align them with lithography patterns made by other methods made in other materials, as we saw from the roadmap, this will complement our existing directions. So as I said before, one of the limitations of these planar processes is that it's difficult to make 3D structures, or it takes a long time to make 3D structures, no matter how you look at it. And there's also some geometric restrictions. So for example, if you use lithography to build up different films, it's easy, it's straightforward to do something that, say, is a pyramid, but it's less straightforward, or because you need the beam axis or the imprint axis to do something that, say, has a reentrant structure like this. So there's also a lot of research in ways to do three-dimensional micro and nanofabrication. And one of these examples is what's called two-photon absorption. And this has been long used for microscopy, and the physical details aren't important. But basically what happens is certain polymers can interact with light in a way that if they receive two photons at once, the excitation of the molecule is much higher, and you effectively get a very selective and a very localized modification in the same way as you would if you were exposing a photoresist. But by this method, you can focus a laser into any point within a certain three-dimensional volume, and based on this local, very sensitive effect, you can, say, zap a particular position. And typically, you have a complex setup with optics and mirrors that can scan the beam in 3 dimensions. And this is also kind of a serial process because you have to move the beam in any point in space. But it's been shown that it can make some pretty cool structures. So this is like a little bull from one of the original papers on two-photon lithography, and you can see that they started from a thin film of polymer, and by rastering the laser, they were able to sculpt out these complex textures. And this, to me, is another kind of, you could say, classic and limiting example of a top-down approach to fabrication, where we can take advantage of a specific and local interaction and selectively modify a material. So in this case, they took they took the polymer, they photomodified it. You could say, for example, they probably had a polymer where they modified it so the place they hit with the laser became the bull, and then they put it in a chemical bath where the rest was dissolved and the bull remained standing. And if you were to look at this paper, you'd also see that they did some studies, for example, for how much exposure time they needed to make certain features, like these circular dots like so, and they also explored the smallest features that they could make by this technique. And one of the sort of underlying principle is that within the focal spot of the laser, there's a thresholding effect that occurs, that when you get two photons to hit a certain point, there's a very sharp transition between the area where you get this exposure and where you don't get any exposure, and this is significantly smaller than the wavelength of the light. So it can beat it by a factor of a few, in addition to being able to be restricted to the focal volume of the laser. And here's another example of structures that were made by this technique. So the last top-down topic that I want to overview is the idea of positioning individual atoms. And again, we can imagine that this is not very scalable right now because you have to pick up and move atoms individually. But in the advent of the scanning probe field, it's one of the things that people have worked on for a long time, and I think is another way of talking or thinking about manufacturing structures at the nanoscale. So to describe this, I'm just going to show a video from IBM. IBM is where the AFM was invented in the 80s, and they've still been working on using scanning probes to manipulate materials.
In a significant move forward in the march toward creating electronic circuits that are thousands of times smaller than today's most advanced technology, IBM is announcing a milestone in the ability to manipulate and understand matter at the atomic level. Scientists at IBM's Almaden Research Center in San Jose, California, have for the first time demonstrated the ability to measure exactly how much force is needed to move individual atoms. Knowing the different forces required to move different atoms will allow IBM's nano-constructionists to figure out which materials should be used for building devices from the atom up. For example, a so-called sticky atom would be used for something that you don't want to move, like a base that you want to keep in one place, while a so-called slippery atom would be used when you want to build something like an on-off switch that needs to move with ease.
10 or 20 years ago, nobody could imagine that we would have today laptops, cell phones, and iPods. I think it's impossible to speculate what nanoelectronics will bring us in 10 or 20 years, but I'm sure it will change our world even more than the iPods we have today.
The force is measured via tiny changes in the frequency of a small quartz tuning fork. This exploration of the realm of atomic scale structures and devices stands to impact the future direction of information technology. This is Jeff Gluck reporting.
So importantly, what they're saying here is it's not really a manufacturing process, but it's kind of like the atomic scale analog to 3D printing, where if they can envision this as a way in, say, a number of years to build individual nanostructures from the atomic level up, you could say prototype what the difference is between a wire if you have atoms in a certain cross-section to another cross-section, and then that might guide your interest in designing a more scalable process to make those specific structures of interest. And if you're interested, there's a paper they published in Science in 2008 that talks about the way that they measure these forces, and it's a nice analog to the idea of intermolecular forces that we talked about before. And this would be, you could say, another way that one might be able to extract information about the interatomic potential between two types of atoms. And a final area of tip-based manufacturing, and this is kind of where we get to the interface between top-down and bottom-up methods, is what's been called dip pen nanolithography. This was invented by Chad Merkin's group at Northwestern maybe 10 to 15 years ago, and they thought of building upon the existing technology of scanning probe imaging, where AFMs were even back then widely used to take images, and combine it with the idea of a fountain pen, where if you, say, make an ink that contains molecules, you can then use the AFM tip like a writing instrument, and taking advantage of the tendency of the right liquid to flow to the apex of the tip, you could then deposit molecules selectively in desired areas. So you could effectively write nanoscale lines using these tips. And in this case, they're showing a schematic where self-assembly of a monolayer is happening locally while you're moving this tip along the surface. And this has been extremely versatile, and in fact is one of the things that they're continuing to work on as a part of the DARPA tip-based program. And there's a company called NanoInc that has instruments that do this. There's one that was just donated by the company to the NanoFab, the LNF here. And one of the dreams is that you could make arrays of many tips that then do this process in parallel. And in fact, some of their newer machines have arrays of large numbers of tips that aren't independently actuated, but are just moved in parallel and can make large arrays of identical structures. And one of the real advantages of this technique is it enables patterning of chemicals and biological molecules. Where lithography is good, e-beam or optical for, say, etching things out of polymers and metals and oxides, you're not really going to as carefully be able to, say, etch a single layer of molecules, or be able to, say, place an antibody at a certain spot. Maybe it's only a 100 nanometer or a 500 nanometer spot, but the versatility to prepare these inks using chemical methods is extreme, and that's why this has really been a breakthrough in nanofabrication. And there are a lot of different methods underway, variations of this. For example, you can heat the cantilever and you can use it to, say, write lines in a thermally sensitive polymer, or there are advanced geometries of tips, for example, using a cone of liquid to, say, focus the assembly or increase the resolution at which the droplet forms. And you can, in principle, also use this to deposit multi-layers, say, make one layer of molecules, and then, say, change the tip or change the ink and put another layer of molecules on top of those. So we're almost at the end here, and what we're going to do in the next few weeks is we're going to review and we're going to learn in depth about bottom-up methods, methods that begin with atoms and molecules and react under chemical or physical circumstances to form nanostructures. And examples of this are chemical vapor deposition, taking chemical compounds from a solution and using it to build a film or to build nanostructures such as nanotubes or nanowires. That's also an analog to crystal growth, because I think nanotubes or nanowires can be considered as nanoscale crystals. And we'll also talk about the idea of self-assembly. I mean, growth of a film or a crystal is in some ways self-assembly, but in a more strict definition, the self-assembly is the process of taking building blocks and engineering the interactions among them, things like electrostatic interactions and van der Waals forces, and also externally applied forces, electric fields, magnetic fields, to control their assembly and control their position and orientation. And we'll talk also about, very briefly, some biological methods that, for example, can be used to control those interactions, so things like DNA and peptide bonding. And what we'll want to get at in the end is an understanding of these methods and an appreciation of the kind of hybrid processes that can be achieved by integrating bottom-up methods with existing top-down methods. So there are a bunch more slides left, which I just put in if you wanted to look ahead and see some of the kinds of things that we'll talk about in the coming weeks. All these will appear in subsequent lectures. And so, one of the, to me, kind of classic examples that's starting to be shown is what's referred to as templated self-assembly, where you use, say, lithography, optical lithography, e-beam lithography, or imprint lithography to create a template, say a physical template where you want some self-assembly process to happen. And then you, say, introduce a solution of building blocks. It could be, say, nanocrystals, or it could be block copolymers, assemblies of polymer chains that we'll learn about later, or it could be particles, such as polymer microparticles. And by controlling the interactions between what's up here and the template down here, you can get ordered placement of these structures. So one example is what's shown here. For example, taking grooves etched in a substrate and introducing a solution of polymer microspheres, or polymer, you could say probably spheres in the 100 nanometer size range, to pack them into this trench. And when the liquid evaporates from this trench, it's favorable for the particles to pack into these areas. And you can see the kinds of structures that can be made, in this case, by just controlling the width of the trench relative to the particle size. And in some cases, you get defects like this, and in other cases, you can control kind of the assembly, the existence of defects to form more desirable structures like so. So that's just one flavor of a mixture of bottom-up and top-down that could perhaps, if you had ultimate control over this process, and say this strip line had a very interesting electrical or interesting optical property, this could be combined with a circuit made by lithographic methods to really bring in an aspect of self-assembly and nanostructures into a scalable large area method. And as we move ahead, I really want to make sure we think about issues of manufacturing, issues of alignment, issues of registry, issues of the specificity and strength of interactions, like what prevents one thing from sticking here and the other thing from not sticking, and what's the probability of that. And also issues such as the density of defects and errors in these structures, and the issues of process compatibility, what temperatures and chemistries one process works in relevance to another process in which it needs to be compatible. We're not going to have deep and thorough answers to all of these for pretty much any of the things we're going to talk about, but I think forcing ourselves as manufacturing engineers to address these topics and state these things in reference to the current state of the art is what will make us try to make an intellectual leap beyond what's going on now, and perhaps will encompass some good things for the project. And